Cosmic Quarks, which is a team of 17 driven black hole enthusiasts who tackled the problem of mass conservation in a system where the black hole devours a star. So please, over to you, Cosmic team.
A very good evening to everyone present here. My name is Akshita Swaminathan and I am the communications leader of Team Cosmic Quarks. Our project is based on the evolution of mass transfer in a black hole companion star system. Following the SSERD tradition, we have a short video by our very own team member Shraddha, and it is a theme that is very famous, and I hope you guys will be able to guess it. So, this beautiful rendition of the Interstellar theme was by Shraddha. Along with me, we have our team leader and assistant team leader as Raj and Bhakti. We've had some exciting few weeks, and our experience throughout these past 5 weeks, including the team meetings, the engagement sessions, have been absolutely great. And I'd like to thank beforehand to all those who worked hard that has led us here to share our work with you. So, a brief introduction to our work. A binary system is one that consists of two celestial objects that orbit a common barycenter. The current work focuses on a binary system consisting of a black hole and a companion star. As we know, a black hole is a region of space time where the gravity is so strong that nothing can escape, not even electromagnetic radiation. They are mainly of three types depending on their mass: stellar, intermediate, and supermassive black holes. An accretion disk is a circumstellar structure formed by diffuse material in orbital motion around the central body. This orbiting material in the disks spirals inward and towards the central body. Our aim is to find the relation that accounts for the mass transfer in a black hole companion star system. By verifying the conservation, we find that there is a discrepancy which we have termed as ghost mass. The black hole undergoes a mass defect due to stellar winds, accretion outflows, and relativistic jet flows. To validate the relation obtained, we make use of a binary system GROJ 165540. To explain the background theory, we have our team leader Raj.
Hello everyone, good evening. I hope everyone's doing fine. Okay, so coming to accretion disk. So basically the process involving the feeding of black holes is accretion. So basically any material that falls inward towards the event horizon it first goes around the black hole in the accretion disk. So what happens is material that go into again revolve around the black hole in the accretion disk, they tend to heat up due to the force of viscosity and friction. So this heating up is of the order of millions of degrees, millions of Kelvin. Also, if you want to look at any black hole, you need to look for its accretion disk because that is the only visible thing that you have in a black hole. The next parameter is stellar winds. So stellar winds is one of the mechanisms through which mass transfer occurs. So basically, it is a fast-moving plasma that is ejected from the surface of the star. The ejection rate and the mass rate is dependent upon the mass of the star. Stellar winds are driven by the photons that are trapped from in the core of the star, and they're trying to escape from it. So basically, the photons escaped in the core of the star that are trying to reach out to the surface of the star carry the stellar winds, and the mass is ejected from the star. The mass loss in the form of stellar winds is absorbed by the black hole, and it eventually goes around the black hole in the form of accretion. The next parameter is astrophysical jet flows. They are relativistic jet flows. They're also called astrophysical jets. These jets are aligned with the spin axis of the black hole. They are long and linear due to the extremely strong magnetic field of the black hole. They are thought to be powered by the material that falls into the black hole, but there are various theories that tell us that these things might be the material that is emitted from the jet might be positron, electron, plasma, and things like that. So scientists have found a lot of these jets at the centers of different galaxies. We have found scientists have found a lot of outbursts occurring at the centers of different galaxies, indicating that there might be supermassive black holes at the centers of different galaxies. So basically, high energetic X-rays and gamma rays are emitted in these jets. The other parameter involved in our research project is Roche-Lobe overflow. So Roche-Lobe overflow is one of the mechanisms that supports the mass transfer in a binary system. So Roche-Lobe is basically a region of gravitational potential in an object. So in the binary system, there is a Roche-Lobe surrounding the two objects, and as one of the stars grows bigger and bigger, the Roche-Lobe grows bigger, and eventually there is a point when the Roche-Lobes coincide. So that is the point where the mass transfer occurs. So in our case, there are two stages of the Roche-Lobe. One is a detached and one is a semi-detached. So when it is in the semi-detached stage, the Roche-Lobe overflow starts. And the mass flow rate is highly sensitive to the fractional excess radius from the donor star. So coming up next, Kirti will be talking about the theoretical construct.
Thank you, Raj. Coming to the theoretical construct we have made, let's see what are the governing equation that will lead us to ghost mass. So basically there are four modes of mass transfer. First one is stellar wind mass loss. So in binary black hole system, the black hole generally accretes only a small fraction of total mass lost by the companion star. To obtain this fraction, we need the mass of companion star and its orbital period, then wind velocity. The next type is mass transfer via Roche-Lobe. For that, what we need is mass transfer rate when stellar radius is equal to Roche-Lobe radius, which we'll be explaining in the next slide. Also, we need radius of companion star and Roche-Lobe radius, then pressure scale height of Roche potential. To get that mass transfer, we need to find isothermal speed of wind around accretion disk, then the pressure scale height of Roche potential. But the major criteria is to satisfy the mass ratio, which is the ratio between mass of black hole to companion star, which must be between 0.5 to 10. The third mode is accreted mass rate. For that, we need total unabsorbed X-ray flux and distance of the source in kiloparsec. These are detectable values. Then we need M Eddington, which is the Eddington accretion rate. It is the rate at which a black hole radiates at Eddington luminosity. That is the limiting criteria for any black hole to start accrete. Then the last one, what we need is accretion outflow rate. So due to the post-shock corona, there will be formation of bipolar outflows, and that is what we call jets. So the experimentally it is proved that only 17% of the total accreted mass will be flowing out, which we obtain from the kinetic jet power. That is what LJet max equation says. Then we obtain the final calculation. Now we have an idea on how much mass is going to black hole and how much is lost by the companion star. Then we combined all the equations and obtained the total ghost mass, that is the unknown mass. To check the credibility of our equation, we applied that to a system GRO J1 65040, which is a stellar black hole and intermediate companion star. And obtained values are, so for the wind mass loss rate, we got with an order of 10 power minus 11, and mass transfer via ROCHE law, we got 10 power minus 5. Then mass transfer accretion rate, it is we found 10 power minus 7, and at last we got the total ghost mass as 3.8 into 10 power minus 8 solar mass per year. And in the coming slides, Shraddha will be explaining about the computation part.
Thank you, Kirti. I hope I'm audible to everyone. So here we have what's been going on in the computational and modeling side of things. So firstly, here's a rough simulation that we did about our system. So this shows the winds transferred from the star and getting accreted around the black hole. This simulation was done by our team member Adiraj using the software Unity. So in order to justify our model and our calculations, we obtained some important plots that could verify if our calculations were in the right area. So our very first graph we have here is the angular momentum loss rate with respect to the radius and the mass. So we plotted this in a 3D format to show the relationship with both the parameters. This graph shows the relationship between the mass ratio and the wind velocity. So as you can see, there is an almost exponential relation, and the graph shows that the stellar winds become negligible for very, very high mass ratios. Here we have the mass of ROCHE lobes versus the pressure scale height, and this is a near exponential plot. So this basically shows the mass loss rate from the ROCHE lobe increases with the pressure scale height of the ROCHE lobe potential. Next, we have the jet power rate versus the accreted mass, and this is a linear relation. This is an important relation because it's important to know how the inflowing mass is related to the outflowing mass. This is a similar plot to before. This is actually the total mass outflow with respect to the accreted mass rate. And since the previous rate was linear, we can expect this relation to also be linear. So in order to do these calculations, we used an IPYNB library, and it's available on GitHub, and so is our Unity simulation. So for further information as to how we obtain these plots and the code involved, do check out our GitHub repository. So let's now discuss what our results mean and what we can infer from this. So the mass discrepancy that we obtained, or the ghost mass, is a calculated value of 3.88 into 10 power negative 8 per year, solar masses per year. And this is quite a feasible value. And our model as such is quite feasible because we are able to make a suitable calculation with respect to a real life system. And in this model, we have considered these three mass transfers. So in the concluding aspect of our project, we conclude that our model has a reasonable chance of existence because we are able to compare it with a real life system. And we are quite confident that there are other systems which can agree with our model as well. And so what is the significance of our ghost mass calculation? So basically, it's important to know that all the mass coming out of the star will not exactly enter the black hole. So there's that mass discrepancy. So calculating this ghost mass value will help us understand the evolution of mass in a black hole with time. And so the future prospects that could improve this model would be including other forms of mass transfers as well, and considering a many-body system and other generalizations, which will make our model stronger and which will work for more realistic aspects as well. For our project, these are the references and research papers that we use to validate our calculations. That being said, we thank you so much for your time, for listening to our presentation. We thank SSERD for this opportunity of bringing like-minded people for conducting research in space areas. And we thank our team coordinators, Rutuja and Priyanka, and of course, our mentor, Sundar sir. And of course, this project wouldn't be possible without all our team members. So thank you to each and everybody who made this possible.
Thank you so much, Team Cosmic, for such a beautiful presentation, and a very special thanks to Shraddha for that beautiful music.
Thank you.
Okay, so audience, it's time for the questionnaires.
Okay, good work, guys. Really, I liked your presentation. So I have a small question. So you talked about ghost mass. Can you tell us what could be the reason for the happening of ghost mass? Any possible reason that you think is responsible for that?
Okay, right. So in response to your question, as you can see, we have considered different mass transfers from the star to the black hole, right? So in these mass transfers, not all of the mass goes into the accretion disk, into the black hole. So in an accretion disk, mass is actually lost in two different ways. One is due to advective fluid outflows, and the other is due to astrophysical jets. So considering this, we conclude that not all of the mass enters the black hole, and eventually some of the mass is lost. So this missing mass is what we're terming as ghost mass. I hope this answers your question.
Okay, so you mean lost? When you say lost, it means it's not going to another body. It is lost somewhere.
Yeah, it's just lost out of the system.
Okay, thank you.
Yeah.
Okay, so thank you so much, guys, Cosmic Quarks, for such a great presentation.